Hey, what's up? It's your old pal, Mr. Cook, and we're going to go through this test review for the Unit 3 Part 2 test. Calculators are allowed on this test, so I'm going to use my calculator pretty regularly throughout this just to show you how quickly you can get a lot of the answers and how you can format them so that it's pretty easy and it gives you all the points, all the um, points to show or credit, for credit and stuff. Okay, so number one and number two, number three, and number four, all it looks like optimization problems. I know that they're optimization because in an optimization problem, it asks you to find the maximum or the minimum of something. Generally speaking, like here's how the problems go: we make a function, and it's relating one variable to another, or maybe several variables together, and then from there we take the derivative. We find the critical numbers, and then we see if any of those critical numbers are going to be, you know, minimums or maximums. If we have further constraints, like maybe there's like some kind of interval that we're looking at specifically, we would also consider the endpoints because the endpoints also must be considered when you're doing optimization because you want to find like the absolute minimum and the absolute maximum over that interval. Okay, so number one, there are 320 yards of fencing available to enclose a rectangular field. How should this fencing be used so that the enclosed area is as large as possible? Maybe I'll zoom in a little bit so I have a little bit more room to work with here. But so it's a rectangle, so we want to make a rectangle, and then rectangles have sides that are the same, opposite sides are the same. So we'll call that x. Call that one x. We'll call this one y, and that one will be y as well. So it says that we want to maximize the area. We want to make it as large as possible. So we create a formula that relates all these variables together: the area to the dimensions that we have, which are x and y. And we can do that by just multiplying those together, because the area of a rectangle is just the perpendicular base and height multiplied together. Now, where it says that we have 320 yards of fencing, so the fencing is going to go along the outside of this shape. So this is really just talking about the perimeter of the rectangle that we're creating with these side lengths x and y. So that total 320 is going to be the perimeter. So we write a perimeter formula. P is equal to 2x and 2y. And then we know that that's fixed. We call that a constraint. So we're going to say that the perimeter is always going to be 320. And typically what happens is, like, if you have an expression that you're trying to maximize or minimize, and the number that you're trying to maximize has like more than one variable associated with it, what you'd want to do is have a constraint, because that constraint will allow you to write one of the variables in terms of the other, and then it'll make this this function a just in terms of one variable. And that makes the derivative a lot easier and finding the critical numbers a lot easier. Okay, but anyways, so we're going to use this constraint and solve for one variable in terms of the other. Maybe I'll get the y value by itself. So subtract 2x from both sides. And then divide by 2 on both sides. So that would get you y is equal to 160 minus x. And then what I would do is I would use this like area formula over here, and that's what I would substitute in. So we have a y right here. It's the same y as this one. So that means that I can replace it with this equation. So that'd be like my next step. Area is equal to x times parentheses 160 minus x. Now, the typical step-by-step process that you go through to solve an optimization problem is now take the derivative, find the critical numbers, and check the endpoints to see which one is the maximum or the minimum number. So I'm going to take the derivative of this, but first I'd probably like distribute that x in there because it's just a little bit easier to manage. So I'd have 160x, and then x times x is x squared. Okay, and then now I'm going to do the derivative. So when I take the derivative, a prime is equal to 160 minus 2x. All right, so there we go. That's setting up pretty nicely. Now what we're going to need is the critical numbers and potentially any endpoints over any interval that's created from the context. Now, I know that X and Y are going to be positive numbers because they're dimensions on a rectangle. So I can already assume flat out that X, whatever X values that I get, they all have to be more than 0. So if I ever get a critical number that's 0, I can exclude that one or any negative numbers because I know that the side of the rectangular area isn't going to be negative. Okay, so then I would look for the critical numbers. So I've got a prime is equal to 160 minus 2x. And I think to myself, okay, so there are two ways to get critical numbers. One is by taking that derivative equation and setting it equal to 0. That seems reasonable here. And then the other one is by taking the derivative equation and trying to find any x values that lead to a d/n/e kind of situation. In other words, like when x is not allowed to be used in the function, maybe it leads to division by 0, maybe it leads to a square root of a negative, something that lies outside of the realm of the x values being real, okay? So luckily, this is just a linear equation, so actually there aren't any situations where I'm going to end up with d/n/e. X can be anything that I want it to be, so I'll exclude that. And it also tells me what I need to do now, and that's just set the derivative equal to 0 and then solve for my x values. Those are going to be my lone critical numbers, just kind of making sure that x has to be more than 0, and then also whatever we've got over here. So I'm going to add 2x to both sides, so 2x is equal to 160, and then dividing by 2, I get x is equal to 80. So that's my only critical number. So now let's see if it's going to be a maximum. So because we're trying to maximize the area, so we use the area formula and a number line. So we put our lone critical number here, 80, and we know that it has to be greater than 0. So let's just set a little benchmark there, 0. And so the intervals that I'm going to look at are the numbers, the x values that go from 0 to 80, and then also from 80 to infinity. And if this thing truly is a maximum for this area, I should get something like this. I should get increasing on the left, decreasing on the right. All right, so let's see what we get. So if we take the derivative equation, let me kind of clear out all the stuff that I don't really need here. There we go. We take that derivative equation and pick a number, any number between 0 and 80. Maybe I'd pick, 60 or something. 160 minus 2 times 60 is 180 minus 120, which would be a positive number, 40. So I know that on the left-hand side in this interval from 0 to 80, it's going to be increasing. And then if I pick a number in the other interval, I'm hoping it's going to be decreasing. If I pick, say, 100, I would get 160 minus 2 times 100. So that'd be 160 minus 200, which, yeah, for sure, that's a negative number, negative 40. So that means that on the right-hand side, it would be decreasing. And, by the first derivative test, I know that this is going to be a maximum because, on the left, it's increasing, and on the right, it's decreasing. So, okay, that's really cool because now I know that the area dimensions I can find. I know that one of them is that x has to be equal to 80. And what were the units? Yards, I believe, of fencing. And then if I go back over to this equation to solve for y, if I plug in 80 for x, 160 minus 80 would give me 80 for y. So y is also going to be equal to 80 yards. Okay, so there you go. That's number 1. And I think we did all right with that one. Okay, so now let's take a look at number 2. All right, here we go. A rectangular area of 10,000 meters squared must be enclosed by a fence. What should the dimensions of the rectangle be if we want to enclose this area using the minimum amount of fencing? So now we're trying to minimize the amount of fencing, and we talked about that already. That's the perimeter. It seems like we're just going over the same kind of problem here, right? We're just given a different constraint. So let's use this information and minimize the amount of fencing, finding the perimeter, in other words. Okay, so here we go. We got the same kind of shape, a rectangle. Opposite sides are the same. Oops. I said opposite sides are the same, and I wrote different sides, of course. So y and y, there we go. The area for this is still the same thing, x times y. The perimeter for this thing is still the same. P is equal to 2x plus 2y. But the difference is that we wanted to maximize this, so we use the a function. Now we're trying to minimize the perimeter, so we're going to use the p function and find the derivative and all that stuff. So the constraint that we are given is that the area is going to be 10,000 meters squared. So this area and the A area in the formula is going to be fixed at 10,000. So that allows us to use this. We call it, again, the constraint, to solve for one variable in terms of the other, and then substitute it in an attempt to use the derivative to find those critical numbers. Okay, so if I wanted to solve for one of the variables, maybe I'd get y by itself. Y is equal to 10,000 divided by x. That's what I would plug in over here, to substitute. So I would get 10,000 over x. And then, now I start up my algorithm that I've worked on and perfected for a long time. And that's take the derivative, find the critical numbers, take into consideration any intervals that we're working with, and then find the absolute minimum in this case. Okay, so let's take the derivative. So p prime is equal to the derivative of 2x is just going to be 2. And then now it's actually maybe a little bit beneficial to rewrite this top part, 2 times 10,000 over x. I'm just going to rewrite that as first 20,000 over x. And then after that, x can be rewritten with an exponent. It's the same thing as saying 20,000 and then x to the negative second. Now, when I take the derivative of that part, that's just the power rule. So I get, and wait a minute, yeah, 2 times, wait, something's up here. Oh, I should have a -1 there. Yeah, sorry about that. Okay, made a little mistake there. Now, if I use the power rule, the -1 gets multiplied by the 20,000 to make it negative 20,000. And then x, and then now instead of writing it as negative to the negative first power, sorry, I'm going to subtract the power away, so I get it to the negative second power. Now, in my quest to find the intervals where this makes sense, like, when I'm again talking about the dimensions, x has to be greater than 0. So that kind of encloses some of the area, some of the dimensions that we possibly could get, limits those. And then also, now I would look for some critical numbers that I get to use. Okay, so 20,000 x to the negative second is the same thing as saying 20,000 over x squared. And this presents one of the critical numbers to us. So if we're trying to look for the critical numbers, p prime, we're going to look for where the derivative is equal to 0, but we also want to look for x values that lead to a DNE kind of situation. And we actually would get that one here, right? Because we can't allow any division by 0, so that means that x equals 0 would be a critical number. We have to evaluate that more. However, we would also immediately exclude it because, our x values are going to be positive. They're not going to be a side length of 0 on the rectangle or a negative side length of 0, negative side length on the rectangle. So that means that even though we just got this from this situation, p would actually be excluded still. X equals 0 would still be excluded. All right, now for the other one, where we take the derivative and set it equal to 0, let's see what x values that we get. So 0 is equal to 2 minus 20,000 over x squared. Then if I add 20,000 over x squared, I get 20,000 over x squared equals 2. And then if I multiply the x squared over on the other side, I get 20,000 is equal to 2x squared. Then if I divided both sides by 2, I would get 10,000 is equal to x squared. And if I took the square root of both sides, I would get x is equal to plus or minus 100. But again, for context, we aren't going to use any x values that are greater than and that are less than 0, so negative. So we get rid of that negative 100. So this is our lone critical number that we're going to explore. So now what we're going to do is check our number line and make sure that this is indeed going to lead us to a minimum amount of fencing. Okay, so here we go. The perimeter equation right here. We're going to use this number line. Our lone critical number is 100 that we're going to use. And remember that we're not going to go below 0. So the two intervals that we're going to look at are 0 to 100, and then also 100 and beyond. So let's pick a number that, so we're going to plug into the derivative now, any numbers in the intervals that we want. So in between 0 and 100, maybe I'd pick 50. So if I took 50 squared, that'd be 2,500. And then 20,000 divided by 2,500 is 8. And 2 minus 8 is going to be a negative number. So it's going to be decreasing on the left-hand side of 100. Okay, let's try that again with another number now, this time in the interval from 100 to infinity. So maybe 1,000 perhaps, or something like that. If I picked 1,000 and plugged it in, so 1,000 and then squared, that would be a 1 with 6 zeros. So 1 and then 1, 2, 3, 4, 5, 6 million, it looks like. So if I divided those out, I would get, let's see, 2 over 100, which would be the same thing as 0.02. And that is a positive number. It's 1.98. So it's going to be increasing afterwards. So yeah, it looks like it is going to be a minimum by the first derivative test. So here's what I would say. I would say that x equals 0. Well, actually, does it ask us? It says what should the dimensions be? Okay. So one dimension is going to be 100, and then the other one is going to be, if I go over to this equation over here, I can find the y value for it. 10,000 divided by 100, that's going to be 100 again. So both of these are going to be 100. And what were the units on it this time? So meters, it looks like. So 100 meters and 100 meters. So it's going to be another square. All right, so there you go. That's the first two problems on this video. I think that I'll stop there and then make another one in a little bit. All right, thanks for watching. Bye-bye.